Welcome to the second lecture on thermodynamics and statistical physics. We will continue our discussion on laws of thermodynamics and its consequences. So first, let us see what does degrees of freedom mean. So let's say an ant is moving along a wire. So to define its motion, we need only one coordinate. If the same ant is moving on a plane, we will require two coordinates to define its motion, and if the same ant is moving on a three-dimensional surface, we will require three coordinates to define its motion. So the minimum number of coordinates required to define the motion of any system is known as degrees of freedom, and the general formula is given by this equation. For gas molecules, we have already seen that they are considered to be rigid spheres, which are three-dimensional entities. So for gases, the expression for degrees of freedom can be modified to this equation, where n is the number of molecules, k is the number of constraints or restrictions, and f is the degrees of freedom. There can be three types of degrees of freedom, that is translational, rotational, and vibrational degrees of freedom. So let us now discuss about monoatomic gases. The gases in which the molecules are composed of single atoms are known as monoatomic gases. For example, you can consider helium gas, neon gas, argon gas, and so on. So these gas molecules can move in along all the three coordinates, so it will have three translational degrees of freedom, and it cannot rotate or vibrate. So total degrees of freedom will be 3. Diatomic gases are the gas molecules composed of two atoms. For example, you have oxygen gas, hydrogen gas, okay? So here, the gas molecules can can move in along all the three coordinates, so it will have three translational degrees of freedom. Also, it will be able to rotate along two coordinates. So if we consider the molecule is kept along y coordinate, then it can rotate along x and z coordinate. Along y coordinate, the moment of inertia will be 0, hence it will not possess any energy, and it cannot rotate along the y direction. So only two rotational degrees of freedom. At high temperature, it will have two more vibrational degrees of freedom, since if the molecule is non-rigid, then we can consider the bond as a spring which can vibrate. So if we apply high temperature, then it will vibrate along its bond, and it will possess two additional vibrational degrees of freedom. So at normal temperature, total degrees of freedom will be 5, and at high temperature, total degrees of freedom will be 7. Now, triatomic gases are the gases in which the molecules consist of 3 atoms. So these atoms can be arranged in a linear way or in a non-linear way. Now, for linear triatomic gas molecules, again, it can move in along all the three coordinates, so it will have 3 translation degrees of freedom. It can rotate along 2 coordinates, so it will have 2 rotational degrees of freedom, and at high temperature, it can vibrate along its bond, so it will have 2 additional vibrational degrees of freedom at high temperature. So at normal temperature, total degrees of freedom will be 5, and at high temperature, total degrees of freedom will be 7. Next, for non-linear molecule, see, it will have 3 translational degrees of freedom, since it can move along all the 3 coordinates. Here, it will have 3 rotational degrees of freedom. Why? Because, say, we consider this axis, let's say this is x-axis. So along this axis, these 2 atoms will not possess any moment of inertia, but this atom will possess the moment of inertia, so it can rotate. Similarly, along all the other two coordinates as well, two of the atoms will not possess moment of inertia, but the third atom will possess a moment of inertia, due to which it can rotate along all the three axes. So total 3 degrees of freedom, and at high temperature again it will possess 2 additional vibrational degrees of freedom. So at normal temperature total degrees of freedom will be 6, and at high temperature it will have 3 degrees of freedom. So next, internal energy. So internal energy is the total energy possessed by the system at the molecular level, and this energy is due to all of these factors. Okay, so translational energy is given by half mx dot square, and rotational energy will be equal to half I omega square, whereas the moment of inertia omega is the rotational velocity. Vibrational energy will be equal to half mx dot square plus half ax square. Electronic energy is the energy possessed by the molecule due to interaction between its atoms. This can be due to electron-electron interaction, electron-nucleus interaction, then nucleus-nucleus interaction. Okay. So let's say initially it is at rest. Whenever we apply some energy, its electronic energy will increase. Now, for transition from one electronic energy level to next electronic energy level, we need around 5000 Kelvin temperature. Now, this much amount of temperature we cannot give at room temperature. So at room temperature maximum, say we can apply from 300 to up to 1000 Kelvin. Okay. So at room temperature we can consider that electronic energy is independent of temperature, because if some amount of temperature we will apply, the molecules, it will undergo transitions within the same electronic energy level. So its vibrational and rotational energies may change, but it cannot undergo transition from one electronic energy level to the next electronic energy level. Okay. So next we have the intermolecular interaction energy, which is due to interaction among different molecules, and this has the maximum contribution to the internal energy. Next we have the rest mass energy. So if we consider the special theory of relativity or the relativistic case, then the molecules will also possess rest mass energy, which is equal to m0 c square. This will also be independent of temperature. So the expression for total internal energy will be equal to translational energy plus rotational energy plus vibrational energy plus electronic energy plus intermolecular energy and rest mass energy. So total internal energy will be sum of all these energies. Now these are functions of temperature alone, and this is function of both temperature and pressure, and these two we have discussed are independent of temperature. So now for ideal gas, we have discussed that there is no intermolecular interaction. So for ideal gas, this energy term will be 0, and total internal energy for ideal gas will be due to translational energy, rotational energy, and vibrational energy plus some constant. So we can say that for ideal gas, total internal energy is a function of temperature, and from the kinetic interpretation of temperature, we have seen that kinetic energy is directly proportional to temperature. So from here we can say that the internal energy will be purely kinetic. Okay, we've already discussed this, and here we have proved it as well. So now, what is the relation between degrees of freedom and energy? So from the law of equipartition, we have seen that kinetic energy per degree of freedom is equal to half kBt. Okay, so for f degrees of freedom, kinetic energy will be equal to f by 2 kBt. For 1 mole of gas, kinetic energy will be equal to Na kBt, because 1 mole of gas will contain Avogadro's number of molecules. So this is equal to f by 2 RT, right? So this is the relation between energy and degrees of freedom. So next, the change in internal energy of a gas. So change in internal energy can be brought about by two ways. First, say we have a thermodynamic system consisting of a piston at rest and filled with ideal gas. So if we apply some heat, then there will be increase in its internal energy. Similarly, to the same system, if we apply some force externally, that is, if we do some work on the system, then also the internal energy will increase. So these are the two ways in which you can change the internal energy of a gas. Now, we have already seen that kinetic energy and degrees of freedom are related by this relation, and internal energy for ideal gas is function of kinetic energy. So change in internal energy can be given by this expression. Okay. So next, the molar specific heat for gases and some important formulae. So we have seen that specific heat for gas at constant volume is equal to 1 by n dq dt at constant volume. Now, from the first law of thermodynamics, we have this expression. So this can be written as change in work done is equal to PdV. Okay, now for constant volume, dV will be 0, so this term will be 0. So from here we can write this is equal to du upon dt. Okay, so next, this implies that internal energy is equal to ncv dt, and also we have seen that internal energy is equal to, okay, now specific heat at constant pressure is given by 1 by n dq dt at constant pressure. So from here we can write that dq is equal to n cp dt. Now from the first law of thermodynamics we can write that so this implies ncp dt is equal to ncv dt plus pdv. Now ideal gas equation is equal to pv is equal to nRT. So if we differentiate it, then differential form of ideal gas equation is pdv plus vdp equal to nRdt. Okay, so at constant pressure this term will be 0, so we can write pdv is equal to nRdt. So if we replace it here dt, and from here we can write that Cp is equal to Cv plus R, which is the Mayer's relation. Okay. Now again from these equations we can write ncp dt is equal to f by 2 nr dt plus nr dt implies cp is equal to f by 2 r plus r is equal to 1 plus f by 2 r. Okay, and from here we can write that Cv is equal to f by 2 r. Now the ratio of these two specific heats is given by gamma, and this will be equal to, so this is equal to 1 plus 2 by f, and from here we have one more relation for Cp and Cv. So Cv can be written as R by gamma minus 1 and Cp can be written as gamma R by gamma minus 1. Gamma is the adiabatic constant. Okay, so from here we get another relation for change in internal energy, which will be equal to nr by upon gamma minus 1 dt, and from ideal gas equation we can write this as vdp on gamma minus 1. Okay, so these are some of the important relations. So next